Hello everyone. Let's take a look at a video by Eric O from South Main Auto Repair and the trouble with Ford Fusion. It's reporting of the wheel speed sensors. You see here that it reports 160 miles per hour before something happens and it starts working again. Eric describes it as working halfway, though it might be just influence of the scales. You see that this graph is on the scale from 0 to 160 and this one from 0 to 30. So this peak is about 30 miles per hour and so is this one. So another quick tip, don't get fooled by the scales. So it looks like the sensor becomes operational again, but before that it reports 160 miles per hour. Why it is 160 miles per hour? Well, the computer sends to the scanner the speed as 1 byte, and the maximum value in 1 byte is 255 in kilometers per hour. 255 kilometers per hour translated to miles per hour is 160 miles per hour, which is reported by the scanner. And what would make the ABS module report such a high speed? It means that that at the input of the ABS module there is some high frequency signal, and that could be a problem with the wiring, could be a problem with the sensor, could be a problem with the ABS module itself. And in this case, with the help of TSB, it looks like the problem is with the wiring. There is a corrosion inside one of the wires that seems to be causing this issue. The question remains, how can corrosion inside a wire cause a high frequency signal at the input of the ABS module? So we'll take a look at that in this video. So how can the high frequency signal appear at the input of the ABS module? Something must be oscillating, and one prime suspect is the sensor. But we need to know how the sensor and systems around it work. So let's take a look at one particular sensor and understand the nature of that beast. So the one that we are going to look at is A1688 chip from Allegro Microsystems, and we are going to take a look at its datasheet. It's a 2-wire true zero speed integrated chip that has a couple of Hall effect sensors in it and a lot of electronics that provide all kinds of stuff. They take the Hall effect signal, they amplify it with a specially stabilized amplifier, automatically adjust the signal offset, automatically adjust the gain control so that the air gap doesn't have much influence on the readings, and after that modulate the current flowing through the sensor itself, and that way the ABS module can read the current and see what's going on. How ABS module reads the current? We can see it on page 3. The current from the sensor goes through a 100 ohm resistor. That voltage drop is being picked up by a comparator with hysteresis, and that goes to the chip inside the ABS module that counts the number of high-low transitions, and from that it deduces the speed. So somehow here we have a high frequency signal. It looks like the sensor is oscillating, and what could cause the sensor to oscillate? And something that caught my eye in the description of the sensor is this feature, undervoltage lockout. The undervoltage lockout turns off the power to the rest of the sensor components if it detects low voltage. at the sensor power supply. So my question is, can a resistor, in this case corroded wire, at the power supply of the sensor cause the undervoltage lockout circuit to oscillate? And to answer that question, we are going to do a circuit simulation. So let's go to an online circuit simulator and create the following circuit. We have a battery, 12-volt battery, powering the circuit, and the load is a 300 ohm resistor. And it is powered when this voltage switch is on. This voltage switch will be on when the voltage at the plus side from this voltage divider is bigger than the stable voltage coming from the Zener diode over here. So when the voltage coming from the battery is good, then this voltage switch will turn on and provide power to the resistor. If the voltage from a battery drops below a certain value, then the voltage coming from the voltage divider is going to be less than the voltage from the Zener diode, and the voltage switch will turn off. So let's do the DC simulation for this circuit in the normal conditions. We see that the voltage switch is indeed on, and the resistor is powered with 12 volts. What do we have at the input of the voltage switch? We have 2 volts in this wire and 1.2 volts on the Zener diode, so the voltage switch should be on. If we change the battery voltage to, let's say, 5 volts, so it's now 5 volts, and run the simulation again, we'll see that there is no voltage at the load because the voltage at the divider is 0.8 volts, which is lower than the voltage coming from the Zener diode, still 1.2 volts. And the voltage switch is off. And this is a good feature when it's working normally. However, what happens if we introduce a resistance at the power supply? And if it's a moderate resistance, like 100 ohms, the circuit still works well. It's going to supply some power to the load. Now let's change the resistance to 350 ohms, somewhat bigger, and see what happens. So we'll run the DC simulation again, and let's take a look at the report. And the report is full of warnings, and at the end we have DC solution fails. So something happened during the search for the DC solution which hints that we have an oscillation in the circuit. So let's do the transient response instead and see what happens. And indeed, all we see is a hash. Let's take a look inside. So this one is the current that's flowing through the battery. It goes from 9 milliamps to 18 milliamps. So the load is being turned on and off repeatedly. Why is that? Well, the voltage at the Zener is still 1.2 volts, but the voltage at the voltage divider goes up and down from about 1 volt to 1.5 volt, turning on and off the switch repeatedly. And so if we are going to go and see what would happen at the ABS module, the load is being turned on and off repeatedly, so we will see a voltage drop, the same pattern at the input of the ABS module, very high frequency switching. And the same thing would happen to the digital square wave coming from this comparator feeding into the ABS module. It's going to be a very high frequency signal. It will be interpreted as very high speed. I'm not exactly sure what it is going to be. The scanner sees it as 160 miles per hour. We know from the code stored in the computer is that a lot of other modules are freaked out by this signal, and that's why they're throwing all kind of codes. It also probably propagates somewhat through the voltage supply. Maybe that causes some battery voltage codes. Also, this high frequency signal monitored by the ABS module probably causes extra load on the microprocessor inside. It might be causing some extra workload for the ABS module, causing some issues with data communications, though if it's fast enough it shouldn't be an issue. So this oscillation causes all kinds of problems, and this is what we see in the codes issued by the computer. So this is what we've considered is one possible cause of an issue, this oscillation due to the undervoltage lockout. It seems to be plausible to me, but maybe I'm not considering some other possibilities. So if you have any comments or suggestions, please let me know. Now, let's say if we didn't have a TSB and had to diagnose this issue or similar issue on our own, how would we go around this problem? And I think it would be a fairly messy and confusing diagnosis. The reason is that if we connect oscilloscope at this point, we will see a very high frequency signal, but it wouldn't be possible to immediately see whether it's coming from the sensor, whether it's coming from the power supply, or if it's some feedback from the ABS module. Likewise, at this point, if we connect an oscilloscope, we will see the same oscillation, but it's not obvious whether it's coming from the voltage line or it's the sensor is oscillating. So what exactly does this mean? It's not obvious. If we disconnect the sensor, then we will see a steady 12 volts at the power supply, because with no current there will be no voltage drop on this corroded wire. However, if we connect a test light to it and it doesn't light up, would it mean there is a problem? I'm not so sure, because this power supply, it doesn't have to provide a strong current. It might actually have an internal current limiter inside it, because it should really never pull more than, let's say, 50 milliamps. So maybe on some designs you will see the test light lit up, on some you don't. Maybe it's a good idea to use some resistor like 300 ohms and connect it to the power supply and see if the circuit can sink about 30 milliamps. Then that would be a conclusive diagnosis. If there is a voltage drop, you know that there is a corroded wire inside. So I would say this circuit is much harder to diagnose than 3-wire sensors or variable reluctance sensors, the standard 2-wire inductive ones.